In this video, we provide a general overview over the memory unit. The memory device is a device to which we store binary information, and this information is stored in order to be retrieved at a later time to use it. Therefore, the memory is the unit where information is available for processing when needed and as needed. The memory unit is a collection of cells that are capable of storing very large amount of binary information. And in digital systems, usually we distinguish between two different types of memories. The very famous random access memory, which is called RAM or RAM, and the read-only memory, which is called ROM. These abbreviations are very well known to everyone. The random access memory, the process of transferring new information into the memory is called write operation. So as if we are writing into the memory. That's when we want to store something in the memory. And the process of transferring information out of the memory is called read operation. So we write into the memory and we read from the memory. However, on the other hand, the read-only memory, where we can only read from this memory, is an example of what we call programmable logic devices. We abbreviate it as PLDs. There are other examples of programmable devices, and these are respectively the programmable logic array, they call it PLA, and the programmable array logic, they call it PAL, and finally the field programmable logic gate array, which is called FPGA. These terms are very well known to people in the field. We will focus in this course on the RAM. We will describe all details about the RAM, and then we will discuss the ROM, and then we will take one example of these programmable devices, which is the PLA. Now, in this chapter, we will use a different symbol for the gates, and these symbols are used for what we call array logic. Now, the typical programmable logic devices may have hundreds to millions of gates interconnected through internal paths. So the number of gates is really huge. Usually we have millions of gates. And in order to show the internal logic diagram in a concise way, it is necessary to employ a special gate symbology applicable to array logic. So we're talking about different symbol that we use in this situation. And the figure below shows the conventional and the array logic symbols for a multiple input OR gate. We used to drawing the OR gate, this shape here, as we see here, that's an OR gate where we are ORing variables X, Y, W, Z, etc. And this will be the output, which is W or X or Y or Z, etc. However, when the number of inputs is very, very large, we cannot put here 100 or 1000 on 1 million lines in parallel. What do we do in this case? We have one horizontal line here, and the variables or the quantities that are ORed together are put as vertical lines, as we can see here, and this will be here W, X, Y, Z. So the output will be W or X or Y or Z. And this is what we use for the array logic in this chapter. So instead of having multiple input lines into the gate, like we used to have here in this example, we draw a single line entering the gate, which is this line here, and the input lines are drawn perpendicular to this single line and are connected to the gate through internal fuses. So usually if we have 100 variables, we connect all of these, and whatever we want to OR, there will be internal fuse here if it is connected, then Z will be ORed. If it is not connected, then Y will not be ORed, will not be input. This will become clear later on. So again, the random access memory, as we said, the memory units stores binary information, and this information comes in groups of bits that are called words. So we store one complete word into the memory. The word is a group of ones and zeros, and it may represent a number or a character, A, B, C, D, or instruction of a program, or any other binary coded information. And most memories use words that are multiple of 8 bits. So usually we find the word 8 bits or 16 bits or 32 bits or 64 bits as an example. And 32-bit word memory is very famous, which means it is 4 bytes. Now the memory unit, in this case, it will consist of 2 to the k words, and it has n bits per word. So n bits per word, as an example, 16 bits per word as an example. So when it has 2 to the power k words, it needs k address lines, because for k bits, we have 2 to the power k combinations, and each combination will address one word in the memory. And because it has n bits per word, the memory will have n data input lines, so we can store a word of n bits, and it has an n bits data output lines, so we can read the word from the memory. And the memory usually has control inputs to be able to write or read from the memory. So that's a block diagram of the memory showing inputs and outputs. To give an example, we consider a memory element, as we can see in this figure here. It contains 1024 words. So we call it 1024 multiplied by 16, which is 16 bits per word. So 1024 words in the memory. So for 1024 words, we need 10 address bits, because 2 to the power 10 is equal to 1024. And the 10 address bits, so this is a memory address in this case, they will have the values from 10 zeros to 9 zeros 1 or 8 zeros 1 0, which is decimal 0, decimal 1, decimal 2, all the way until decimal 1021, 22, and 23, when all the bits are ones. So we have 10 ones. So the binary address, the first one, will be the address of the word number 0 in the memory, and then word number 1 in the memory, and number 2, etc., etc. And the memory content, as we said here, it's 1024 multiplied by 16 bits. Therefore, each memory word will have 16 bits. So the first word can be 1011, 0101, 0101, 1101, and so forth for the rest of the words.